Today we're looking at a linear parent function, and we're going to start to look at transformations. Alright, so a linear parent function is, any parent is the simplest form of the function. So if you're talking about a linear function, normally we look at linear functions in the mx plus b form. But the simplest form will be where the slope is 1 and the b is 0. So that would be a y equals x. That is the parent function for a linear function. So it's the simplest form. There's nothing added, subtracted, multiplied, or divided there. It's just in its simplest form. So if I take a calculator, here I'm at y equals. So I want y equals x. Okay, so you can look at the table. Let's start with -4. So -4 is at -4, -3, -3, -2, -2, and so on. Since the input is equal to the output, they're going to be the same. Y is equal to x. Okay, and let me graph this. So at -4, I'm down at -4, -3, -3, -2, -2, and so on. Again, if you're thinking about slope and y-intercept, the slope is 1 over 1, up 1, right 1, and the y-intercept here, there's no number, so it would be 0. So you start at 0, 0, up 1, right 1, or down 1, left 1. Alright, so this forms my parent function of a line. That's the original starting place before we start adding, subtracting, multiplying, and dividing to that parent. Okay, so from the parent function, we need to find some attributes, starting with domain and range. Now in Algebra 2, we're looking at domain and range in 3 different forms. Sometimes you'll see it in inequality form, sometimes you'll see it in interval notation. Quite often in the upper math, you'll see it in set notation, so we're going to start to look at that as well. Okay, domain is all of the x's. Okay, and this is my x-axis. So if I take a look at all of the x's, there's an arrow going all the way to the left, an arrow to the right, so it's including all real numbers. So in inequality notation, that's going from -infinity from the left all the way to +infinity to the right. So everything to the left, everything to the right is -infinity to +infinity. Notice that I have x. So anytime you have inequality notation, you're going to have the variable is in between this number and this number. So the one on the left, if it's always the smallest number, and the one on the right is always the biggest number, then the inequality notation that you use there, the symbols that you use, can always be the same, with the exception of if it is open circle or closed circle. So it's not actually equal to. Alright, interval notation. Interval notation is similar to inequality without the symbols. So if we're going from -infinity to +infinity, in interval notation, it would simply look like this. -infinity to +infinity with a comma in between. Set notation has braces. So you're going to do a brace, and then you're going to say all x's such that, and then you're going to rewrite the inequality notation. So all x's such that x is in between -infinity to +infinity. And then you close it off with some braces. Okay, let's take a look at range. Range is all the y's. So all the way from the bottom of the function all the way to the top of the function. So you can see the arrows, not only are they going left, but they're also going down. So all the downward numbers, and then the opposite arrow is going to the right as well as up. So we can say as well that the inequality notation for the range is going to be negative infinity to positive infinity, but with range it's all the y's. So the bottom of the function is negative infinity, the top of the function is positive infinity. In interval notation, it would look exactly like the domain, negative infinity to positive infinity, with parentheses. Set notation. So here we're talking about all the y's such that you have negative infinity to positive infinity, and then close it off with braces. Okay. Is the function increasing or decreasing? So if you take a look at the function, it is in fact increasing. And let's see if I can move this down a little. Oh, here we go. There we go. Okay, so this is an increasing function because the movement is left to right. So I'm going to say, yes, this is increasing. It is not decreasing. Sometimes if it is not going on to infinity, we can say it's increasing from this to this or decreasing from this to this. It all depends on the type of function. But when we're talking about linear, it's either going to be increasing or decreasing if it goes to infinity. Intercepts. So where does it cross the x-axis? It crosses at 0, 0. But since this is the parent function, it hasn't moved from 0, 0. So the y-intercept, where it crosses the y-axis, is the same place. All right, so that's all the attributes for the parent linear function. Let's take a look at some transformations. Okay, so let's start off with the first transformation. So whenever you take inside the function and you're either going to add a number or subtract a number from it, that will translate it left and right. So let's just take a function here. I'm going to use function of x is equal to x minus 1. So just a simple function. If I want to translate this function to the right, that is only when a is negative. So if you take a look at a, there's a right there. Okay, so we're saying if I want to, let's say, take the function, let's make a negative, so I'm going to say negative 5. And we're going to subtract 5 from the function. So basically what this means is I'm going to replace x in the original function with x minus 5. Okay, so it's x minus 5 minus 1, which is x minus 6. All right, so if I go back to my calculator, I'm going to say my original function is x minus 1. My translated function is x minus 6. So what happens to the graph? So there's my x minus 1. My x minus 6, you can see part of that graph there. What happens is it's moving it 5 units to the right. So in my definition, when it say it translates right, if a is negative, that is a true statement. All right, so let's try going the other direction. So let's make a positive 5. So that means I'm going to replace x with x plus 5. So x plus 5 minus 1 is x plus 4. So if I go to my y equals, and I'm going to change x minus 6 to x plus 4. From the original function, it moves it to the left. Okay? So that's how that works. All right, the next one has an addition or subtraction on the outside of the function. So it translates up when a is positive, translates down when a is negative. All right, so let's see what this looks like. So if I take the entire function and let's add 2. So the entire function is x minus 1, and then I'm going to add 2. X minus 1 plus 2 is going to be x plus 1. All right, so let's see how that translates it. Original function is x minus 1, and now I want x plus 1. Original function, and look what happens. It takes it up 2 units. So every point on the original function, you can translate up 2 units on the graph. So that's what's happening there. Okay, so if we want to go down when a is negative, we could say f of x minus 2 is x minus 1 minus 2, which is x minus 3. So we go from the original function, the movement is down 2. Okay, so that's what that looks like. So we've gone left, right, up, and down. Let's take a look at what happens when you multiply by a number. So if you take the function and you multiply within the actual function, let's see what happens there. Let's multiply. It says it stretches horizontally if a is in between 0 and 1. So that's a fraction. So in between 0 and 1, let's just take 1/2. So if I multiply the x by 1/2, you're replacing the x in the original function with 1/2 x. So it looks like this, 1/2 x minus 1. So if I do 1/2 x minus 1, there's my 1/2 x. Okay, so what's happening here is it flattens. So you take the original function and you're actually flattening it out. So it is called a stretch horizontally. If you think of a horizon from left to right, it's taking that original function and stretching it out that way. I like to think of it as flattening it. Let's do flattens. All right, it compresses horizontally if a is greater than 1. So if we try multiplying by a number bigger than 1, let's try 2, it'll be 2x minus 1. So there's the original function. There's my 2x minus 1. So this one's actually pushing it up. So it's horizontally compressing it, like if you take a beach ball and you press it together with your hands from left and right. Okay, you push it in. So it kind of pushes it to where it pushes it up, I guess I would say. Pushes up. All right, then we have a vertical stretch and a vertical compression. So if you're multiplying by a number out in front of the actual function, let's see what happens there. Let's go back to green. Okay, so if I'm doing, let's do 1/3 times f of x. So 1/3 times f of x would be 1/3 x minus 1/3. If I distribute 1/3 into the x and the -1, that's what I get. Okay, so it would be 1/3 x minus 1/3. Here's your original function. Okay, so then it's sort of flattening again. It's as if you are sitting on the beach ball now. Okay, if you're sitting on the beach ball, it actually gets wider from side to side. So that is a compression vertically, vertical compression, and we use the term it gets wider. Think of the beach ball when you sit on it. Vertical stretch is when you multiply by a number greater than 1. So it would be like 3 times f of x, which would be 3x minus 3. Okay, so this one is a vertical stretch up. So vertically is up and down. So when you vertically stretch up and down, it's as if you are pulling on, let's say, gum, and you're pulling it up and down. That would be a vertical stretch. And in math language, they say it narrows. Okay, last two. So we have a negative. So what happens when you apply a negative to the function? To the inside of the function, it reflects over the y-axis. So this would look like, let's see, f of negative x. So you're replacing x with negative x. So it would be negative x minus 1. So there's my original, and you can see that is flipped over the y-axis. It's a reflection over the y-axis, as if you took both sides and folded it along the y-axis. They would meet exactly. All right, and then the last one is a reflection across the x-axis. So this would be a negative on the outside of the function. So it would be negative x minus 1, which is negative x plus 1. So that's just a simple change. There's your original. And so now if you folded the graph along the x-axis, it would flip right on over and land right on top of the other. Okay, so that would be a reflection over the x-axis. So these are all the transformations. These are used for every function that we go through, and we're going to go through a lot of functions this year. So this is a good handy chart to keep around. Okay, so we'll be working through all of these over and over and over again throughout the year. We're just starting with linear, moving on to different functions at a later time. All right, I will specifically use the warm-up time to look at linear functions again, and then you will have an assignment to work.